Okay, as you know, we've done limits in 2D, right? And basically you do like a left side, and then you do like a right side, and you try to see if they agree, right? So in 2 dimensions, limits are pretty straightforward. You've got a curve. You've got a particular x in mind, maybe it's 5. And you're trying to see if the graph f of x approaches the same y value from either side. Well, when you start thinking in 3D, things change a little. The question's the same, okay? The question's the same, like what z value is being approached as we come towards a point. But the problem is, all the different directions we can come from, there's no longer a right side and a left side. If I pick any point on this surface and put my finger on it, there are an infinite number of ways to arrive at that point as we travel towards it. Okay? It's kind of like saying, here on my floor, right, there are many tiles. If I choose one tile and color it red, right, there are many different directions I could approach that tile from. I can come from this way, I can come from this way. And it's not just 2 sides anymore, it's an infinite number of sides. Does that make sense? Yes or no? Okay. All right. So the first problem I actually gave you was a continuity problem. Now, can you guys tell me, why is this not continuous at 5? Why is f of x in our little blue and red picture there not continuous at 5? What's the reason? F of 5 does not exist, but the limit does, right? So we would say it's not continuous there. It has a point discontinuity, right? Or we call that a hole. Okay. The same is actually true for this surface you're looking at. Okay. There's a hole in it, and we're going to find that hole. Okay, so as we've seen, a surface in R3 can be described using functions that contain up to 3 variables. The ones we use are x, y, and z, or r, theta, and z, or rho, theta, and phi. Right? The Cartesian, the cylindrical, the spherical. So right away, I just want to jump into limits and how you would tackle them. Okay? So this first question just says, let's discuss the continuity of this surface. So continuity, fortunately, has pretty much the same meaning as it always has. If there's a break in the fabric of this curve, we'd like to find it, and we'd like to know what kind of break it is. Is it like a permanent tear that can't be fixed? Or is it just a hole in the surface that can be simply plugged up? Okay? Okay, so the first thing you want to do is just look at the expression. Can you think of any x's and y's that would cause, and you're supposed to pick an x and a y, that would cause the 0 on the bottom? X squared plus y squared. Will that expression ever yield 0? Yes. It will, right? So that would happen if x and y were both 0. You guys understand? Okay, so you're choosing an x and a y that makes this expression either undefined or indeterminate. So let's take a look at the surface itself. If you look at the surface, you should be able to study this and understand it. Okay? Why does it look the way it does? Why is it bent the way it's bent? Why is it curved the way it's curved? Why is it rising where it appears to rise? All those questions can be easily answered by simply picking, listen, pick a z equals 0, and then write x squared over y squared over x squared plus y squared equals 0. Cross multiply it and solve it. And you'll see that it really just represents a single point. If you pick z equals 1 and you cross multiply it, you'll see what this surface is just above the plane. If you want to, you can pick x's. If you pick like x equals 1, this greatly simplifies into a rational function or something. It's like it's got y squared on top and then 1 plus y squared on the bottom. You can think about what that curve would look like, and then you can trace it out on it. So you should study this, or at least plug in an x and a y, and like plug in x equals 10 and y equals 10, and understand why this point right here is so dang high. Like why is it way up on the z direction? Okay, so by plugging in larger numbers and smaller numbers, we kind of play around with it and see if you can kind of map this out. Okay, so topographically it's ugly and it's messy, but I think you can understand it if you start playing around with plugging in numbers. Okay? All right, the job of this function is you give me an x and a y, and and I'll tell you how high off the desk it is. That's the whole purpose of this function. Right? Okay, so you can see that it looks continuous everywhere, right? Like at your first glance, you're like, oh yeah, nice sheet right there. If I was walking along that thing, it might be steep, but I won't fall through any holes or anything. So it certainly looks continuous everywhere. However, if we let x and y both be 0 at the same time, we get 0 over 0, which is one of our indeterminate expressions. From your experience, you should probably suspect a hole at the origin. In other words, we think this origin point is probably a hole after all. So if you went to the origin, you'd fall through. Okay? As you can see, f of 0, 0 doesn't exist. Or you could say it's undefined, right? So we actually do have a discontinuity somewhere. But I wouldn't suspect it to be like a gaping asymptotic barrier there. You know, it's not like the whole curve is ruined near x equals 0. It's just one point may be missing. So graphically, I use WinPlot to do this. You can download WinPlot. It's free. Graph this on WinPlot using the 3D mode. And I picked an angle that looked like we could understand the curve. And we just want to see if that's a hole right there. Actually, we want to prove that it's a hole. Okay, so we would say that basically it's a hole because when you're coming from any direction towards the origin, as you travel along this surface, whatever path you take, right, whether it's this path, or this path, or this path, or this path, as you follow the contours of this surface and you try to head your way towards 0, 0, they all have the same destination. All of these have the same exact destination. But once you get to f of 0, 0, it's gone. Okay? So what we need to do is show that all paths lead to 0. Z equals 0. That's what we need to prove. All paths lead to z equals 0. All right. So no matter what path you take to 0, 0, you always, all those paths seem to have a limit of 0. So path is the word that goes here. All right. By the way, there's 6 ways to state that, at least. Okay? One is you can write LIM, x goes to 0 and y goes to 0, of the function z equals 0. Or you could put limit, as x and y both go to 0, of f of xy equals 0. Because f of xy means the z function, is what it means. And then here, limit x goes to 0 and y goes to 0, and then just write the expression equals 0. Or you can use this alternate notation, xy goes to 0, 0, and then use either z or fxy or x squared y squared over x squared plus y squared. So these are just new notations. But how do we actually prove that this limit is 0? Please don't sleep in Calc 3. Thank you. How do you prove that the limit is 0, especially if you didn't have that picture, right? That picture showed us that everything kind of converged down onto the origin, right? But how do you prove that? That's very important and very challenging, okay? Listen, how do you show in 2 dimensions that a limit exists? How do you prove it? What do you have to do? You have to do the left limit, right? You have to get a number. Then you have to do what? The right limit. And then you get a number. And if they are what? The same number, you've proven it, right? You haven't proven continuity, but you've proven that the limit exists. Doesn't that mean then that we have to try every single one of those paths at the same time? Or at least at separate times, like do an infinite number of limits and prove that all of them come out to 0? That's what it means. You understand the problem? Okay, so this is just problematic. We don't have the time to do an infinite anything in our lives. You can't even blink an infinite number of times before you die. See the problem? Okay, so to get around this issue, we need to maybe play around with the function. All right? So I think think this problem would be a lot easier to understand in cylindrical coordinates, cylindrical coordinates. If we can convert our equation to cylindrical, there's only two directions, towards the origin and away from the origin. So I think this would be a lot easier in cylindrical coordinates. We just need to check that any radial path that approaches the origin yields a z-value limit of 0. So instead of thinking, hey, I'm going to travel this xy path and this xy path, why not just say, hey, let's just all go to r equals 0. Then it's just like an inner approach kind of thing. Okay, so you're already pretty comfortable with conversion, I hope. But x squared can be written as r squared cos squared, and y squared can be written as r squared sine squared, you know. And the same thing on the bottom, r squared cos squared plus r squared sine squared. And then there's this limit out front where the point xy, the destination, you know, is 0, 0. Let's go and update that too. If we're going to be changing all the x's to r cosines, why don't we write this as r cos r sine goes to 0, 0. So I know it's awkward, but you write lem, and then under it, r cos theta, r sine theta goes to 0, 0. You'll notice that the top is basically got an r to the fourth, and the bottom only has an r squared, right? So you can actually reduce this thing quite a bit. So you have limit r cos theta, r sine theta goes to 0, 0. And then the top has an r to the fourth, the bottom has an r squared. And this looks like cos squared sine squared over cos squared plus sine squared. Well, cosine squared plus sine squared sounds awfully familiar. That's just 1. Good riddance to the denominator. I'm not too sure what to do with the top, but I don't think it matters anymore. Notice that the r to the fourth and the r squared reduces anyway. In other words, the only thing that survived this was r squared cos squared sine squared, which doesn't even have a denominator. So just like in the world of 2 dimensions, when these things sort of factor and cancel down and there's no denominator left, you're dealing with a whole, right? So now all we have to do is let r cos theta and r sine theta both go to 0. Okay? Now listen, the thetas are the same thetas, the r's are the same r's. R cos theta and r sine theta, they're both involving the same exact value of r and the same exact value of theta. The only way on earth that both r cos theta and r sine theta can simultaneously be 0 is if r is 0. Okay, so I'll say that again. This expression, r cos theta is 0 and r sine theta is 0 at the same time. You know there's not two thetas where sine and cosine are both 0, right? Sine is 0 when the angle's theta is 0, but cosine isn't, you know? And cosine and sine never quite agree on their roots, you know? So the only way this could make any sense is if this is just the statement r goes to 0. So theta's gone from the problem. This can be simply replaced with r goes to 0. So here's our new problem to think about. I ran out of space, but you can write it on a new line. Just the green. The limit as r goes to 0 of r squared times blah. R squared times who cares? Right? Who cares what's here? R is going to 0, it's r squared times something. What's the answer? 0. Right. That's a proof. We proved that whatever radial path you take towards the origin gives us a z of 0. And we just did an infinite number of calculations all at once. So we did. Very cool. So literally, no denominator remains, so we don't have to worry about 0 over 0 cases anymore. So that's what goes in this blank, 0 over 0. So no matter what direction we take, we seem to be approaching the z value of 0 as we approach x equals 0 and y equals 0. The fact that the r cancels out of the denominator, and there's no longer any r's in the denominator, shows us our discontinuity was like a whole. It's just like Cartesian world in 2D, when that root on the bottom goes away, you know it's a hole, right? Okay, so I would say, we were asked to discuss the continuity of this surface. I would say this surface is continuous, except at the origin where there's a hole. We've proven it, right? It's not a graphical thing. Really, honestly, what does it prove to look at a picture and make a prediction? Nothing, right? You can't trust your eyeballs or your measuring skills to prove anything in life. So, let's take a look at this next problem. And I think, for some reason, oh yeah, the solutions still have blanks in it. I was hoping you guys have the ones that have some blanks in it. You guys have blanks on this problem, right? Okay, cool. So, the function is not continuous. Where is it not continuous? So in this problem, we're just finding a limit. So it's a little bit less thinking. Just, here's the problem. Here's the limit we're going to find. And I think, actually I think you should cross this out up here. Just find the following limits. I already changed the expression, I think, on a couple problems. So, okay, let's look at the first one. Limit as x cubed y over x to the 6th plus y squared. What is the limit of that when x and y go to 5 and 2? Well, if you look closely at this problem, when when x to the 6th plus y squared is set equal to 0, you actually get a result for that. You actually learn that if y is either plus or minus x cubed, right? If y is either plus or minus x cubed, wait, is there a typo on this one? Oh shoot, I didn't think I had typos on this. I was trying to look for an obvious discontinuity. Oh, I'm looking at there's two problems here, sorry. Let's look at this one. That's the one I intended to do. There we go. I see what happened. Notice that when y is negative x cubed, that bottom is going to be 0. That's a problem. Okay? That's a real problem. How big of a problem? Is it like a whole sort of thing? Or is it more serious than that? So what we're going to do is understand that there is some kind of a tear in the graph along the curve y equals negative x cubed. There's like a tear in the surface. It could be a permanent tear. But notice the point that we're studying. The point we're studying is 5, 2. Even if the surface is torn along the curve y equals negative x cubed, it shouldn't affect us because 5, 2 isn't on the curve y equals negative x cubed. In other words, 2 is not equal to negative 5 cubed. So it shouldn't matter. And we can just substitute. So this problem is very simple. You let your x be 5. You let your y be 2. And you basically just get 250 over 127. So what we're saying is, yeah, there's just probably a really bad tear in the graph on a certain path. But it doesn't matter to us because we're not studying that path. We're studying a portion of the surface that is fully intact and continuous, actually. So that's the answer. So that's real simple, right? Sorry about the duplicate problems there. Let's look at this next one. If you plug in 0 and 0, just off the bat, you get 0 over 0. So I'm suspecting that there's a hole at 0, 0. Let's find out. So the limit might not exist, you see. Remember what it meant in 2D? If you get 0 over 0, it means the limit might not exist. But it might exist. It depends on if it's a hole or a break, or like an asymptote. Okay, so what happens if you just do one at a time? This is very, very important. If you just let x be 0, that's like traveling along the y-axis. Okay? And if you travel along the y-axis, you will reach the point 0, 0 eventually. So I'm just going to make x 0 first. Okay? And when I do that, I get this expression. Limit as x and y both go to 0 of 0 cubed y over 0 to the 6 plus y squared. So that just comes out to 0. On the other hand, you need to try to take other paths towards the origin. You have to actually study an infinite number of paths, right? So you could let y be 0 now if you want, or, since that's probably just going to give you the same answer, pick some other path that passes through 0, 0 I can think of all kinds of graphs that pass through 0, 0. Lots of them. Y equals x squared, y equals x cubed, passes through 0, 0. Sine x passes through 0, 0. I can let y be any of these. All of those paths run right through the origin. Okay, so you're going to replace your y with any expression you want. I'm choosing x cubed because I think it's interesting. Why? If you let y equal x cubed, watch what happens. You get limit as x goes to 0. There's no y anymore. X cubed over x to the 6th plus x to the 6th. In other words, you get limit as x goes to 0 of x to the 6th over 2x to the 6th, which comes out to a half. Interesting. I picked a different path that goes right through the origin. Y equals x cubed does pass through the origin, you have to admit. Why did I pick it? I thought it'd be interesting to get the degrees to match, top and bottom here. So by picking x to the 3rd, I actually got this very interesting problem. It didn't give me like 0 or something like that. It gave me a half. So what does it mean that when I made x equal 0, I'm traveling along the y-axis towards the origin, I get 0. But when I come from a different direction, I get a half. What does it mean? It means the limit doesn't exist. Yeah, and it's not continuous either. So because we got two different results, we have proven that the limit doesn't exist. We've proven. So what happens is you end up finding more than one way through 0, 0, and you have to be a little creative. And in this particular problem, fortunately, we got two different answers. Actually, a good thing we got two different answers, because if everything I seem to be trying keeps giving me the same answer, I've got to keep on trying to find that counterexample that doesn't give me that answer. So for example, if I just keep making x 0 or y 0 or whatever, I'm just going to keep getting 0, 0, 0. I'm going to be tempted to think that limit's 0. But I just picked a path. It's kind of an interesting one. I picked a path through the origin that gave me a limit of a half, which defies the fact that the limit could be 0, and it shows the limit actually doesn't exist. So now you can see why this is a tricky topic. You have to invent a path that gives you a different answer if you suspect the limit doesn't exist. And my first thought on this problem was that the limit would exist. I thought it was a hole, kind of like that last problem we did back in example 1. But it wasn't a hole, and it's because of this path right here. Y equals x cubed. You can see clearly that it's not the same as going along the line y equals 0, or y-axis x equals 0. So I just picked these two paths. There's other things you could have tried. So. Okay, are there any other questions? Or are there any questions? Okay. Okay, so because of the half guessing, most teachers don't expect you to do 50 of these on a test. Okay, they just expect you to find a couple paths that sort of disagree, and then you say, well, the limit doesn't exist. Or maybe I'll just on the test, I'll say, hey, prove that this doesn't exist. That way you know it doesn't exist, and you're just trying to find the paths. If you suspect that the limit does exist, then you're in for a real treat. You've got to somehow test all the infinite paths. And I showed you how to do that by switching to cylindrical. But that doesn't always work either. If you want more ideas on how to sort of prove that a limit does exist, you can go to this website. And I know this isn't super professional to put a, what do you call it? What do you call these? It's just not like one of the sources a teacher's supposed to give you, You're supposed to give like more professional, websites and stuff. But listen, not many people have addressed this issue. So I found this website where a person asks, hey, how do I tell if a multivariable function has a limit? How do I prove it has a limit? And this guy gave a really good answer. Try different paths. Use polar coordinates. He means cylindrical in this case. Use a delta epsilon proof, which we haven't learned. Or use algebra and theory. The only ones that would apply to you are the use polar coordinates. But if you want to read through this sometime, you can. Okay, let's try one more real quick, and then the bell's going to ring. Find the limit of x cubed y over x cubed plus y as you go from as you go towards the point 1, negative 1. Well, if you plug in 1 and negative 1 right off the bat, you get 1 cubed times negative 1 over 1 cubed minus 1, which basically gives you negative 1 over 0. In fact, it yields 0 over 0. No, it yields, it basically yields undefined anytime you let y and x be opposites, right? For example, if you let y be 5 and x be negative 5, oh no, that's not true. Whenever x, I meant to say whenever y equals negative x cubed, yeah, whenever y is negative x cubed, that bottom's going to be 0, see? Okay, so we suspect that the limit doesn't exist. And when you suspect the limit doesn't exist, you just need to find two paths that give different answers. So I'm going to replace all my y's with negative x cubes. And the top gives me negative x to the 6th, and the bottom gives me 0. And this expression is undefined always. I don't care what x and y are going to. Even though I already chose basically this little limit down here should say, update this please, right here. This should say x comma negative x cubed, right here, under the LM. So if negative x cubed is going to 1, negative 1, that's just the same thing as saying x is going to 1. So let me fix that here. And this is undefined always. So this one doesn't exist. This is a true D&E, just like the last one. I don't need to find two paths. That expression is always undefined. So basically, there's an infinite number of paths rather than just a left and right side. Switching to cylindrical did help. Back on example 1. And for other ideas, you can check that website. But it probably will be a little beyond you right now, and that just means I won't test you on it. Have a great day. You'll get a worksheet on this.